Hello everyone, my name is Chandralil Chakraborty. I am from University of California, Santa Cruz, and today I'm going to talk about explaining SSD failures using anomaly detection. Now, while SSDs are more reliable than traditional HDDs, they suffer from shortcomings like they wear out non-linearly with device lifetime, they accumulate bad blocks and are prone to infant failures, which leads to data loss of data availability, unstable system performance, each of which are costly, including the cost of maintenance and over-provisioning. Now, this motivates us to predict SSD failures. Now, predicting SSD failures is inherently a challenging problem due to the class imbalance. SSDs fail rarely, and hence the dataset we looked at contained only 4,000 failures compared to 30,000 healthy drives. And the data from failed drives were reported far fewer. As a result, we had 40 million healthy data points compared to 15,000 failed data points identified as outliers. We had large number of features, 21 to be exact, and as a result you can see that the data looked very clustered. As you can see, there was very difficult to separate. And now, compared to prior work, our work proposes a new one-class autoencoder model that improves accuracy by up to 13%. It also enables adaptability to previously unseen failures and enables us to interpret the results. The key idea is to train the model on the majority class while ignoring the minority class for the model. Our idea is to create a latent representation of what a healthy drive looks like. This prevents overfitting to the source set of known failure types seen in training and also improves the generalizability of the model to predict unseen failure types. Additionally, we introduce new feature selection technique and perform hyperparameter tuning. Now, the dataset we looked at contained 30,000 unique drives collected from Google's data centers spanning 6 years. It contained around 40 million reports with 4,000 failures, and some of the failures were put back into production after repair, which we treated as a failed case. In total, there were 21 features collected, which included drive characteristics, status lags, and error counts. Now, to separate out the features, to pick the important features, we implemented 8 different algorithms and using 3 different feature selection methods, filter, embedded, and wrapper techniques to highlight the most important features in our data set, which you can see from on the right. And we ratified it with the engineers in the field. Now, we chose ROC to compare our performance because it's a good measure of separation for imbalanced data set consistent with prior work. We used 3 baselines, random forest SVM and neural network, to compare our work with prior work. Now, compared to prior work, our techniques provide 7.6% improvement over baseline technique, and our technique is not independent of the number of failed drives seen during training. Now, we used the reconstruction error of the autoencoder model to divide it per feature to compute the reasons for failure. If an error was more than average error per feature, it was listed as reason for failure. Now, from the figure you can see that the frequency of an occurrence of an error. So you can see that most frequently reported reasons are cumulative bad block and correctable error, which leads to SSD failures. However, it only accounted for 30 and 35% of the failed drives. This shows that while there exist important features which lead to SSD failures, only a combination of several features lead to accurate prediction. Okay, so to conclude, our work provides a comprehensive analysis of machine learning techniques to predict SSD failures. And we show our approach based on one-class machine learning models outperform prior work by 9.5% by significantly improving the accuracy of failed drives. For dynamic environments, our one-class techniques improve over baselines by 13%, and we also introduce one-class autoencoders to enable interpretability of our model predictions. Thank you so much.